So thanks so much for that, Dirk. And I don't really talk very much at all about a theory of punishment, or about Tom Hill, or about any of that stuff. So I probably won't have much to say about it here either. I should just kind of try to place my work in touching a nerve into a broader context. And the broader context is this, that there are a lot of people in the wider world who have not had the benefit of many, many years of taking philosophy courses and making finer and finer and finer distinctions. And it worries them a lot when they hear that either your actions have to be uncaused or free will is an illusion. Because, not surprisingly, they think this bears upon the criminal justice system and how we treat criminals. And what they understand when philosophers say these rather remarkable things, or in some cases, I guess we would call Sam Harris a neuroscientist with quotes, and this really worries people. And I often had, normal, very smart engineers, physicists, and whatnot say, what on earth are the philosophers talking about? And so I would make all these distinctions between this sense of free will and that sense of free will. And quite honestly, it has diminishing returns in that context. Now, it may, within a philosophical context, be productive and rewarding and rich, and I can't actually speak to that. But I can tell you that in the wider community, it confuses people no end. And bringing in Kant and acting, outside of the physical nexus, but not really having this does not work. And so after tiring of trying to do what you might call outreach, I decided, look, I'll say a very little bit about the fact that the expression free will is full of semantic bear traps. And then I just want to put it aside. And instead I'm going to talk about something else that is reasonably well defined at the behavioral level and at the neurobiological level, and something that we actually understand in a certain amount of detail. So it's not that I'm offering a theory of free will, it's that I have completely despaired of much of the conversation in philosophy about free will. And so that's the main motivation. And the other thing is that there are really sort of two general domains that have had an impact on how I think about this. And one, of course, has to do with the criminal justice system. And although we all recognize that the system rooted in the British tradition has flaws, probably of many kinds, it also embodies a tremendous amount of wisdom. And it's actually very useful to go to the criminal law itself and to go to specific cases that are important for the criminal law to see how things are handled, as opposed to making up weird thought experiments. So that's one source of inspiration for me. The other has to do with development of humans and other animals. And neural development is really a very fascinating and interesting business, both at the behavioral level and with regard to the neurons themselves, and how neuronal structures change as a result of experience, being approved of certain things and being disapproved of certain things. And it was very obvious from everything that the child development people said, as well as what the reinforcement learning people said, that basically we treat ourselves as causal organisms when it comes to inculcating good habits. And Aristotle understood that perfectly. As interestingly enough, so did Darwin. And so even when you're an adult and your project is to inculcate a good habit, to stop smoking, as the case may be, we count on the causality of certain structures, and now we kind of have a good idea of at least which structures they are, if not in detail how they work. We count on those structures being causal. If my basal ganglia are not causal, but just wildly indeterministic, then it's kind of hopeless for me to try to develop a certain good habit that I think I might need to have. And there would be no point in my approving and disapproving various behaviors of children if I thought that causality was off the map. So those are the kinds of things that have had a significant effect really on how I think about things. And part of what I want to do today, and just perhaps because it reflects my bias and my passion, is to tell you a little bit about the neurobiology of self-control. And one of the reasons, of course, is that it's relevant to the topic at hand, but also for a kind of wider methodological reason, and that is, you know, in neuroscience, we often think that what we really ultimately want to do is to be able to make links between behavior, systems, and below systems to macro circuits, to micro circuits, to neurons, and to neurochemicals. And interestingly, in the case of self-control, we can already see those links. Now, I'm saying links, I'm not saying, you know, full, rich explanations, because that we do not yet have. But links there clearly are. And so I'll just say a little bit about some of those. Okay, so I'm starting with just a very fast observation, which you all, I think, appreciate, and that is that it's very easy, once you are attentive to it, to realize that many, many animals have self-control. Now, let me just back up for a quick moment and say what I mean by self-control. Typically, there are a variety of considerations. One is that you can defer gratification in the sense that you can postpone an immediate reward now for a larger reward later. You can cancel an action that has been started. You can multitask, although that's not as important, but also that you can suppress impulses that are inappropriate in the circumstance. Those are the usual things we look for. And the behavioral neuroscientists have been very clever, as you're about to see, in figuring out how you can test for example, stopping an action in a rat or for deferring gratification in a rat. Now, you might think that's really hard, but I'll show you how it's done, and it's very elegant and very beautiful. So that's what I mean to a first approximation by self-control. If you back me into a corner and we start splitting hairs about this meaning and possibly that meaning and so forth, I'll just go quietly nuts, because we can't do much better than that right now. That's about as good as it gets. Though the meaning of it will become more precise as time goes on and the science gets better. But it's premature, and if I may invoke an old joke of Dan's, it's premature to try to define too precisely some of these expressions now. Okay, so there's a fox predator, there's a cougar, you can see a group of wolves trying to bring down a caribou, immense self-control. Bringing down a caribou for wolves involves something that's very, very frightening. The caribou has a tremendous kick. It also has antlers. And the wolf could just, hightail it and run home. They don't. And then, of course, what you'll see are some service dogs, some golden retrievers that are trained to get money out of an ATM. And this is one of those, you might think of it as an Aristotelian habit, but the point that's so interesting is that you can create these habits by exploiting the reinforcement system in ways that people have understood for eons. It's just that we now kind of know a little more about the detail. May I have the next slide? So what we want to know next is something about the neurobiological difference between not having control and having control. And I'm suggesting that this actually falls along a spectrum, and that in some cases, if someone is terribly tired or terribly hungry or terribly frightened, their control may be diminished. So let's go to the next slide. So this is just the reminder about there being many levels in the nervous system. So Terry Sainovsky and I designed this in 1992 in an explicit attempt to replace what we felt was an inadequate account of levels by David Marr. So David Marr had a tendency to talk about the hardware. But it's very clear that when it comes to the brain, you can't talk about the hardware, because there are many different levels of organization, all of which are, in a certain sense, the hardware, but which operate on somewhat different principles. Okay, so the next slide. Now, the marshmallow test that Walter Mischel ran, we talked about this yesterday, so we'll take the next slide. So in the next slide, this is work done by Moffat and Caspi in, can we have the next slide? There we go, okay. I wanted to add some numbers to the story. So Moffat and Caspi ran longitudinal studies on kids in New Zealand, but instead of just using the marshmallow test, they used all of the kinds of tests that I indicated were relevant to self-control. And over the long haul, and this is just one way of looking at the data, because it's important not to get too excited about these differences, but it's also important to recognize that there are differences. In the top fifth of the group, we're going to compare them with the bottom fifth. And you can see there are many more health problems in the bottom fifth with regard to these measures of self-control. More substance abuse, lower incomes, higher crime conviction rates, and higher numbers of children reared in single families. Those are the criteria they happen to use.
You mean single parents?
Yeah. Or reared by single parents. So, this is just a sample of the kind of work that's being done on self-control at the behavioral level. So now we're going to go down, so the next level. So it's been known for a very long time, long before there were very good imaging techniques, that people with prefrontal damage often suffered a loss of impulse control. They would be socially inappropriate under many conditions. They would be inappropriate with regard to their impulses regarding themselves, their eating behavior, and so forth. And of course, the question was whether it was really just the cortex that was involved here or not. One thing you should know is that when the lesion, shown here in black, this is from the Damasio's, when the lesion occurs in adult life, basically you can expect some loss of self-control for things that are not desperately serious, or at least not within traditionally what we would call the moral domain. If, however, the damage occurs during childhood, you will see a much higher risk for doing frankly immoral behavior. So we know that the PFC, the prefrontal cortex, plays an extremely important role in regulating self-control. And people have long really been curious as to what that is. And bearing the Walter Mischel kind of test in mind, we can have the next slide. The question was, we'll have to use animal models to understand at a finer grained level. So Trevor Robbins in Cambridge has been doing studies on self-control in rats. And I want to just give you an example of the experiment for deferring gratification. So you have yourself a rat, and he's in you put him into his test space. You have a food tower there, and all he has to do is nose poke a button, and out comes a pellet. So he learns to do that. That's very easy for a rat. They can do that in a trial. Now you put in a second tower. And now the rat if the rat nose pokes the second tower, it gets 5 pellets. All right, so you can see the relationship to the marshmallow test. So how do you test now for deferred gratification? And the answer is very clever, and that is you introduce a delay between when the animal pokes at the high pay tower and when the pellets are delivered. And the question is, can the animal wait for the high paying delivery? And the answer is very interesting and not desperately surprising, and that is lots of them can. They sit there and they wait. Some of them cannot. And you can repeat it again and again, and there are some that just seem incapable of it. And interestingly, there was one, for example, Zippy, who just kind of like never got it. He knew that it was supposed to be there. It was like Damasio's patient EVR. But on the other hand, he always went for the other tower, the low-paying tower, and his offspring were all the same. So that indicated something that you would want to study further. So then Robbins also looked at whether an animal can stop an action once he's started. Like you are driving into an open parking space, a kid's ball rolls into it, can you stop? And most people can, although you will be interested to know that addicts have a much, much more difficult time doing that. And we'll get back to addiction and brain changes with addiction in a moment. So the way he set that up was to have the food tower there. The rat has to run to the food tower, give it a nose poke. But if he hears a tone as he approaches the food tower, he must stop. Otherwise, he gets nothing. Rats can learn to do that. And now what you do is you vary the proximity to the food tower of the rat. And the closer he gets, the harder it is for him to stop. So some of them can stop here. Some of them can only stop here. And if they get closer, they just do it. And so here's an interesting question you might want to ask at this point. Is self-control exactly the same? That is, can the rats who can defer gratification, are they the same rats as the rats who can stop and cancel an action? And the answer is very interesting. There is an overlap, but not a perfect overlap. Some are really good at canceling, but not so good at deferring gratification. This provoked Robbins to do the next thing, which of course turns out to be hugely important for those of us interested in the reward system, and that is they charted the pathways involved in each of those behaviors, deferring gratification and stopping an action. There is overlap in the pathways, but they're not exactly the same. Okay, so now I want to go to the next slide, and now I want to say a little bit about addiction. And that's relevant at least because addiction has direct implications for self-control. And it is a huge, massive policy issue in almost every country in the world. And it's of the greatest importance that we understand the nature of addiction. It ruins untold numbers of lives, costs untold numbers of dollars and euros and pesos and what have you. So addiction has been a focus of study in neuroscience using many different approaches for a long time. And what I want to do is just to sort of give you a sample that I think is very important and that helps us understand a little bit about the tension between self-control and compulsion in the case of addicts. Now, in this slide, and I really am going to have to go up to one of the screens because otherwise you're not going to really understand it. So in this slide, I first of all want you to look at the top panel, and you'll see a blue line. Now, the blue line represents mood. And so what we're imagining is that the animal or the person begins at an emotional homeostatic point here, and he's given some cocaine. And so his mood goes up. He feels pretty good about that. And we have a good idea where the cocaine goes and why he feels good, but that's another part of the story. So normally that's what happens. You feel good, and then it's just the way your brain works that you then go down. All right? So there is a correction in a way. It's sometimes thought of as opponent processing in the way that it is in the visual system. So it's kind of like if you're going to feel really good, you're going to come down. Now, what actually happens when you come down? What goes on in your brain? And the answer is very interesting, and that is there is release of a very particular neurochemical called corticotropin releasing factor, which is a stress hormone. So when you feel anxious, like I'm about to ask you a really hard question, I want you to stand up and deliver, right? Makes you feel anxious. Your stress hormone just spiked. And it's not a good feeling, it's a bad feeling. And okay. Here comes the stressor. And all animals will do whatever they need to do to get rid of the anxiety. Okay, so our friend here had one dose of cocaine, he had a hedonic response, and let's suppose he does this, and incidentally this could be cocaine, heroin, and for those of you who are thinking about this, nicotine, which is one of the most potent addicting substances going. All right, so after a while, there's more of this and more of this, and what we see happen after a while is that the hedonic response is less and shorter, and the anxiety response, the stressor response, is deeper and longer, and that happens successively. So by the time you're here, you're barely getting any hedonic effect from your substance. You're getting a deep anxiety effect from massive amounts of stressors, and so it goes. And all this shows down here is that particular areas are recruited kind of in an aggregate fashion to add to that anxiety. So initially you have one shot, the VTA, in one of the subcortical structures. It's important for reinforcement learning. It's a reward center, so to speak. The VTA releases dopamine that helps you feel good, and then it releases CRF, stress hormone. And after a while, you keep doing it, and now the nucleus accumbens is doing it as well. So you can see that increasingly, by the time you get to being a really serious addict, all of these areas, after you have the substance, are making you anxious. And so it's a sort of feature of addiction that we can now sort of understand, at least to a first approximation, something about the state of mind that makes it very difficult for addicts to stop taking the substance because they want so badly to get rid of that stress hormone and that feeling of anxiety. And we'll go on just to, I only have a couple more slides. Now, an important feature, no, go back, yeah. An important feature of the reward system is dopamine, which is a neurotransmitter that binds to very specific receptors in order to have its effect. And in this slide, what I want to show you is 3 control brains of a human, a monkey, and a rat, not shown to scale, needless to say. This human, it has been abstinent from cocaine for a couple of months, but was a very, very serious cocaine addict. The monkey could self-administer cocaine as often as he wanted in the lab, and he liked it. It was great. I mean, they do it, and they also like alcohol, especially in the late afternoon. I'm not joking, that's actually true. And then there's the rat. Now, what are you looking at here? Well, you're looking at a cross-section of the brain so that you're able to see deep structures. And you're looking at dopamine receptors of two kinds, the D2 and the D3 receptors, which are important for habit acquisition and reward learning. And they have been tagged with a radioactive substance so that you can see them without actually killing the animal. So we're using positron emission tomography to do this. And the basic result is that you're seeing a big reduction in D2 dopamine receptors in the cocaine addict, even though he's now been abstinent. You're still seeing him, which means it's harder for him to learn stuff. Not just harder for him to quit, it's harder for him to learn all kinds of habits of other kinds. The monkey also, there's our cocaine addict monkey, big diminution in receptors, and similarly in the rat. So you might want to say, oh yeah, but you know, a couple more months, wouldn't they all be back to normal? And there's some controversy about this because we all know the brain is very plastic and has these properties of recovery and so forth. But at the moment, there are quite a number of people who think that these results are pretty much permanent. And so this, I think, gives us a lot of insight into the importance of finding ways of dealing with a really important public issue. I mean, now we're not talking about a funny issue in some possible world, in some possible universe. This is real. And these are real data. And these data show us that at a very deep level, there are changes in the nervous system that are quite profound and that have a really big effect, not just on the substance in question, but on other aspects of learning as well. And I can give you chapter and verse on that, but I don't want to go on too long because it's hot and I think people are starting to. So I'm sorry I don't talk about a theory of punishment very much, except to say that, of course, we can tweak the criminal justice system as it stands. I think it's just, you know, kind of playful but irresponsible to say that we should just give up the criminal justice system. I mean, or that people should not be incarcerated. If we had treatments, it'd be a wholly different story. We don't. For almost nothing do we have treatments. There's 600 known, approximately, nervous system diseases. For how many do you think we have an adequate intervention? Essentially none. So anyhow, that's my spiel. It's not very philosophical because it's really placed very centrally in this actual social world that we actually live in. So anyhow, I can talk a little bit about situationism and all that later, but I don't think I want to do that now because I think it may be time for questions.